Yellowstone volcano. Despite the vast number of disaster movies or articles discussing whether the Yellowstone supervolcano in Wyoming and Idaho will catastrophically erupt each year, we confidently know that it is currently incapable of producing any form of a volcanic eruption, including a very small one. We know this due to the nature of Yellowstone's massive magma chamber, which has been estimated to contain, depending on the source used, between 4,000 and 11,500 cubic kilometers of magma. In any given magma chamber, the magma is divided primarily into two categories, solid and melt. The solid magma represents semi-solidified to solidified rock full of crystals which form due to its slow cooling at depth. If solid magma was to exist in a basaltic composition magma chamber, it would form a rock type known as gabbro. In contrast, the melt represents what is typically associated when you try and picture magma. As much like its name implies, it represents molten rock in a liquid state. At volcanoes around the planet, one way to determine if an imminent volcanic eruption is theoretically possible is to determine the percent makeup of a magma chamber in terms of melt and solid material. It is fairly well known that a section of a magma chamber needs to be at least 35%-50% melt by volume to be theoretically capable of producing an eruption. Since the Yellowstone supervolcano's vast magma chamber contains somewhere between 5% and 15% melt, this means that it could not produce an eruption anytime soon unless a fairly fast and drastic change occurs to its magma chamber. This is why we do not believe that Yellowstone will erupt at any point in the next 1,000, perhaps 10,000 years. If you compare the maximum melt percentage measured at magma chambers in various volcanoes listed below, you will note that only the systems which are above the aforementioned 35% threshold have erupted at some point in the last 1,000 years. A new scientific paper which is referenced on screen was published, and it showed something quite surprising. This paper suggests that Yellowstone's magma chamber melt percentage maximizes out at not 15% but instead 28%. You might see this figure and say, well, what's the big deal, that figure is still below 35%. And you'd be correct, but there is a potential problem. You see, the Long Valley supervolcano in California has less than or equal to 27% melt, and thus Long Valley volcano should be theoretically incapable of producing a volcanic eruption at the present. Yet, Mammoth Mountain, which under some definitions could theoretically be considered part of the Long Valley caldera, last produced an eruption via a phreatic explosion a mere 700 years ago. Or, between 1980 and 1982, a batch of magma intruding underneath Mammoth Mountain advanced from a depth of 10 to 3.0 kilometers depth before it solidified, still remaining there today and causing large amounts of carbon dioxide to seep onto the surface, forming dead tree zones on sections of the mountain. While this magma probably originated from a distinct magma chamber completely separate to the one at Long Valley, in some models, it was claimed to have originated from Long Valley's magma chamber. Yet, if an eruption was theoretically not possible at Long Valley, how did it get so close to the surface? Therefore, we are left with a few possibilities. 1. Perhaps we have incorrectly estimated the amount of melt in the Long Valley caldera's magma chamber, and there exists somewhere a part of a magma chamber with greater than 35% by volume melt. Possibility 2 is that we have measured its melt correctly, but that our 35% threshold figure is wrong, and might need to be lowered under certain conditions. Possibility 3 is the simplest explanation in my opinion, with the magmatic intrusion underneath Mammoth Mountain not representing a batch of magma from Long Valley's magma chamber but rather its own distinct magma chamber.